Welcome back to Material Atomics. I'm Michael Shiloh.
I'm Anastasia.
Today, I wanted to discuss something that's been popping up in the comments section a lot lately.
And he hasn't told me what it is.
Yeah, so a lot of people come to this channel because they've been really interested in material mediation of light and gravity. And historically, the routes that were taken to model such a situation were fluidic in nature. So I'm thinking about some of the venerable forefathers like Maxwell and Descartes, and people trying to explain phenomena in terms of some substance which is forming vortices. And obviously, our model of the atom has some elements of fluidics to it.
Vorticularness,
right? Of course, our shell. But today, I wanted to consider other phases of matter that might be analogous and that we should probably be considering also, because I love water. I think water is the most amazing chemical in existence in that it can do so many different behaviors depending on its phase state. And so I wanted to get your thoughts on the idea that perhaps some of the interesting qualities, the structural aspects of the atom, why does it form filaments, for instance, in some circumstances? Why does it form a nucleus and a shell under other circumstances? And could there be other phase analogs of that subatomic fiber that could propel it to behave differently under different circumstances?
Okay, my first thought is that it doesn't form filaments and shells and nuclei. It is that the substance that makes the atom in a universe that contains many atoms, by necessity takes that form. Do you know what I mean?
So like the whole conspires to create the individual substructures.
I mean, that sounds pretty spooky, but it's hard for me to imagine, like, are there loose filaments? Like, can you just have a filament that's, like, on the ground?
I originally specified that one tenet of the hypothesis is that there are no monomers possible.
Like, I can imagine a filament that has broken free of one atom and is retracting into another atom.
You know, let's go back to a different gauge of existence. So let's say atomic phenomena. When you have monomeric matter, so let's say an atom, just right, or a gas in space, right? It generally exists in an ionized form, or quite often, anyways. And so when I think about atoms that are just loose, particularly when they're not subject to the pressures of gravity, and they're what we would say in outer space, which is a weird way of putting things, but it's easy for people to think about it that way. When that pressure is relieved, when you depressurize an atom, it becomes ionic, right? Under our model, that means that its shell is expanded so much that it can actually conduct electricity, shell-to-shell electricity, at a great distance. And I wonder if there isn't a phase of the fiber which is similar to that. Likewise, in something like the nucleus, where there's a great convergence of fiber from the shell in a small volume of space, that the motion wouldn't slow down and the surfaces of those fibers wouldn't compress so that you get something that's more ice-like.
So you think that they would compress, sorry.
I'm just exploring the idea that seems like a place where that sort of thing might happen.
I mean, that makes sense on the level of, to connect it back to water, right? Because you studied water in the context of bacterial spores, and you have liquid water that exists on the outside and it flows, and yet when you put it into a constrained environment where it's being pushed on or pulled on, however you want to see it, by the walls of the container, then it starts to take on these like very strange forms where it's still water, it's at room temperature, but it's no longer liquid in the sense that it flows. It turns into what amounts to a room temperature ice.
Mm-hmm.
And so what you're saying is that if you liken the structure, if you liken the material of the atom to a fluid, right? So let's say that inside of the shell, there's a component of it that flows, just loose and flows. But then, like water, it has a surface tension. And at the surface tension, at the place where there is surface tension, it no longer flows like water. It's actually a cohesive thing that's no longer a fluid. Because as far as I understand fluid dynamics, there's a difference between bulk and edge.
Yeah, I think this is why one of the reasons I love water as an analogy for the subatomic fiber is that water really is like a fiber, right? It enmeshes with one another. It can bear tension under certain circumstances, right? And that's part of the reason that we push back against the word particle in our modeling, is because particles don't have that ability to tug on one another, but waters do, right? And I think that's what you're getting at. Is in my academic work previously, I was looking at how water was able to bear tension under these confinement circumstances, which don't give them a way out, right? And the nucleus seems like it's also a situation where there might not be an out. And I guess what we're going to start moving towards, and actually our most recent conversation with Jeff Yee cracked open the nucleus for the first time, but we need to start considering how the nucleus is participating in some of the other the shell phenomena, right? If the nucleus is informing the shape of the shell to some extent, then the nucleus could also be driving some of the shell behaviors like electricity, magnetism, light, gravity, things like that.
Well, there was also the really weird conversation, or the really weird comment that John Williamson made during one of our podcast episodes, where he said that in a proton, the nucleus and the shell are the same size. In a hydrogen atom or something. Or did he just say that for the proton? Like
I don't remember that.
He implied, and I remember being very perplexed by it, which is that when you have this resonance, that you lose the distinction between the pure shape or the pure size of the nucleus and the size of the atom itself. And with Jeff Yee, the conversation was kind of about the fact that the shape of the nucleus is affecting the shape of the orbitals. And so if what you're seeing is the fluid of the fiber running over the shape that's inside the nucleus, then all of a sudden you have a direct line between the outer shape of the atom and the inner structure as it like vortices onto the inside. There's some kind of crazy shape that happens there, and that's what gives you the orbital dynamics.
Yeah, I don't remember John talking about it specifically, but I know that Dewey Larson wrote a really interesting treatise on this idea that everything that we know about the nucleus is, well, in his day, right? This was before some of the bigger colliders and the quarks and all of this, but the idea that essentially the early Rutherford experiments really just tell us the mean location of the atom. They don't necessarily tell us anything about its substructure, which is an interesting case, right? I think it's called the case
against the nuclear atom.
Mm-hmm,
yeah. I mean, I think that's accurate. And so from what you're saying, it basically sounds like there is good reason to treat the model that we have as being a fluidic model. But what that means is that you have to take into account all of the things that you would take into account with a fluidic model, which has to do with all of these other edge cases, because a fluid does not always behave as it does in bulk. When you're down on single molecule interactions, fluid is not a real useful way of modeling it, because when we think of fluid, we're thinking of bulk dynamics.
100%. And so I just want to open up the idea, because I want to open up the idea that we should examine some of these other phase behaviors in searching for the way that this fiber is accounting for the phenomena that we observe, the atomic phenomena that seems spooky or magical that we're trying to explain with this model. So let us know what you think. I'm curious, your ideas. Obviously, the point of these conversations is for us to develop the model better, to hopefully be able to explain more phenomena with it, or to come up with a totally different model that's better capable of explaining them. So far, we've been able to explain the things that we've approached. And so let us know what you think. Let us know what other phenomena you would like to see interrogated using the model, and we'll try to do that on subsequent conversations.
Sounds good. See you next time.
See ya.